Yesterday we applied the Laplace transform to an entire differential equation, and we solved the result of that and isolated the quantity called capital F of s. We noted yesterday that if we could just undo the Laplace transform and turn capital F of s back into our function y equals f of t, then that would give us a way to solve the differential equation to find the solution without ever having to use method of undetermined coefficients or variation of parameters or guessing a solution of the right format or any of that nonsense. Today, that's what we're going to talk about. How do you undo the Laplace transform? How do you reverse it? The inverse of the Laplace transform is our official name for the reversal of the Laplace transform. For example, someone says that the Laplace transform of the function 1 is equal to the function 1 divided by s. This would be equivalent to saying that the inverse of the Laplace transform, represented by the script L and a -1, of the 1 over s would bring us back to the function 1. If I undo the Laplace transform, if I apply the inverse of the Laplace transform to 1 over s, then I get back the function 1. So diagrammatically, I could write it something like this. The function f of t equals 1. The function capital F of s equals 1 over s. To go forward, I would use the Laplace transform. To go backward, I would use the inverse of the Laplace transform. Now we have our table from 2 days ago for the forward direction Laplace transforms, and you can basically use that exact same table and just flip the L on the left to an L inverse on the other side to get the table that we need for the inverse Laplace transform. For example, the inverse Laplace transform of 1 over s is equal to 1. The inverse Laplace transform of 1 divided by s minus a is equal to e to the a times t. So let's practice using the table to undo the Laplace transform on, for example, f of s is equal to 1 divided by s minus 4. So this has a format 1 over s minus number that's very similar to the entry labeled C in my table. If I want to find the inverse Laplace transform of 1 divided by s minus number, the table says take e and raise it to the power the subtracted number multiplied by t. Let's do a few more complicated examples. Somebody wants the inverse Laplace transform of f of s is equal to 1 divided by s cubed. So let me consult the table to see if I can find an expression which is similar to the one that I have in its format. Now the entry in the table that seems the most concerned with 1 divided by s to a power is the entry here in B. I'm looking for the inverse Laplace transform of an expression which has s to a power, the power 3, or 2 plus 1 in the denominator. Now the table tells me that if I have s to the power 2 plus 1 in the denominator and 2 factorial in the numerator, then the result of the inverse transform will be t to the power 2. Now that's not exactly the same thing as what I have. I have the 1 over s to the power n plus 1. I have the s to the power 2 plus 1 in the denominator, but I currently don't have the 2 factorial in the numerator. So what I'm going to do is I'm going to artificially put a 2 factorial in the numerator, but then I'm going to divide by the 2 factorial that I just put in. That way, nothing has changed from what I had before. This quantity is equal to what I started with. So I'm going to factor out that constant multiple of 1 over 2 factorial. And now I'm taking the inverse transform of something which is identical to one of the entries in my table, 2 factorial divided by s to the power 2 plus 1, and the table says that that is the same thing as t squared, t to the power 2. So use the table, but bear in mind that oftentimes you're going to have to make some minor adjustments to make your function be an exact match to one of the entries in the table. Alright, here's an even more complicated example. Suppose that we wanted to find the inverse Laplace transform of s divided by s squared plus 2s minus 3. Now scrolling back up to the table, I seem to be in big trouble. There are 4 entries in the table which have a denominator which contains an s squared. But none of the entries in the table have a denominator that contains both an s squared and an s, like my expression does. So when you have a rational expression that doesn't quite match any of the entries in the table, the idea is to try partial fraction decomposition. I'm going to take my rational expression, I'm going to factor it, and then I'm going to try and split it up as a sum of 2 simpler fractions. So I'm going to go ahead and use the Heaviside cover-up method, which says that for s plus 3, which zeroes out at s equals minus 3, cover up the factor corresponding to s plus 3, and plug s equals negative 3 into the result on the left side. So that looks like negative 3 divided by negative 4, which is 3/4. For s minus 1, which zeroes out at s equals positive 1, cross out the s minus 1 on the left side and plug s equals positive 1 into the remaining factors. So I get positive 1 over 4. So instead of trying to find the Laplace transform of the original function, I'm going to try and find the inverse Laplace transform of the decomposition on the right side. Which is much easier because now I can split this up using linearity. Now looking back at the table, when I'm taking the inverse Laplace transform of 1 divided by s take away number, the table says that the result will be equal to e to the power of the subtracted number. So I can think of 1 over s plus 3 as s take away negative 3, and therefore the inverse Laplace transform is e to the power minus 3 times t. The inverse Laplace transform of 1 over s minus 1 would be e to the positive 1 times t. And this function would be the inverse Laplace transform of the rational expression that we were given in this problem. But in order to find it, in order to use the table, we had to decompose the rational expression so that we had a sum of the functions which were in our table. For an even more extreme example of this, let's find the inverse Laplace transform of 1 divided by s squared plus 1 multiplied by s squared plus 4. So in this case, I have 2 quadratic factors in my denominator, which cannot be factored any further without using complex numbers. So that means that Heaviside cover-up method cannot be used. So I'm going to have to do this the old-fashioned way of guessing a linear numerator and another linear numerator. When I clear those fractions by multiplying through by the least common denominator, I get 1 on the left side, the quantity ax plus b times the quantity s squared plus 4 in the second position, and the quantity cx plus d times the quantity s squared plus 1 in the third position. And that's a big whoopsie on my part. These should really be s's, since that's the variable in this expression. So let's go ahead and multiply all of this out. We have 1 is equal to as cubed plus bs squared plus 4as plus 4b. And we have cs cubed plus ds squared plus cs plus d. Now once again, I'm going to look at terms based on who contains S3, who contains variable squared, who contains variable, and who contains constants. Similar to what we did with method of undetermined coefficients. So for the s cubed terms, we have an a plus c, but that's equal to 0 because I have no s cubed terms on the far left side. For s squared, we have b plus d, and that's also equal to 0 because there are no s squareds on the far left side. For s terms, we have 4a, and it looks like c, and that's also equal to 0 because there are no s's on the far side. And for constants, we have 4b plus d, and that's equal to the 1 on the far left side. Now the first equation implies that c and a are opposites. If I plug that into the second equation, that implies that 3a is equal to 0, so a itself is equal to 0, and therefore c must also be equal to 0. Equation number 2 implies that b and d are opposites. And if I plug that into equation number 2, I get 3b is equal to 1, so b is equal to 1/3, and therefore d is equal to negative 1/3. So using that data, what is the decomposition of the expression that I am working with? The decomposition is equal to 1/3 s squared plus 1 plus negative 1/3 s squared plus 4. So if I want to find the inverse Laplace transform of this expression, I can now use linearity to turn this into 1/3 inverse of 1 over s squared plus 1 minus 1/3 inverse of 1 over s squared plus 4. So let's look at our table again and see if our table tells us anything about how to invert the transformation on these two expressions in the parentheses. The one that seems closest to what we have is the entry number D. In entry D, we have a quantity which has a number in the numerator and then s squared plus number squared in the denominator. Now if I rewrite the expressions that I have to match the format in the table a little more closely. In the first expression, I have 1 divided by s squared plus 1 squared, since 1 and 1 squared are exactly the same thing. But in the second entry, instead of 4, I have 2 squared. But I don't have the 2 that I would need in the numerator to represent the k in the numerator in the formula of the table. So what I'm going to do is I'm going to artificially put a 2 in the numerator at the cost of also introducing a 1/2. Now, the expressions in the parentheses have the right format to use the entry in the table, and I get 1/3 inverse Laplace transform of the first fraction, which is sine of 1 times t, minus 1/6 inverse Laplace transform of the second fraction, which is sine of 2 times t. Now that we've practiced finding the inverse Laplace transform of a few functions, let's go ahead and see what it would look like to use the Laplace transform and its inverse to solve an initial value problem. So I'm going to begin by applying the Laplace transform to both sides of the differential equation. Now I'm going to cut to the chase and apply and use linearity to split this up as the transform of y double prime plus the transform of y is equal to root 2 times the transform of sine root 2 times t. Now for short, I'm going to nickname the Laplace transform of y as capital F. And with that notation, I'm going to rewrite this expression. The Laplace transform of y double prime is the same thing as 2 s's multiplied by capital F. Take away 1 s multiplied by the original function at 0. And then decrease the number of s's and increase the number of derivatives. Meanwhile, the Laplace transform of y given here on the left side of the equation, I'll just call f for short. Using the table, the Laplace transform of sine of root 2 times t is equal to the number root 2 divided by s squared plus root 2 squared. So let me go ahead and start cleaning this up. And I'm going to use the fact that I'm told that y of 0 needs to be 10 and y prime of 0 needs to be 0. So I get s squared times f minus 10 times s minus 0 plus f is equal to 2 divided by s squared plus 2. The next thing that I'm going to do as part of the overall process is I'm going to algebraically solve this for f. I'm going to isolate the quantity called capital F. So this is going to involve me collecting all the terms which contain f, banishing all the terms which do not contain f, and then dividing out this s squared plus 1. Once we've isolated f, the next step is to apply the inverse transform to both sides. When we apply the inverse transform to capital F, then that will recover the function y, which is the solution to the IVP. Now, in order for that to be possible, we're going to need to break down this first fraction, because it's currently more complicated than any of the entries in the table for our inverse Laplace transform. So I'm going to break it down as a linear ax plus b over a quadratic plus linear over quadratic. And I'm going to go ahead and clear the fractions. We get 2 on the left side, ax plus b, s squared plus 2, plus cx plus d. Oops, I'm using x again. Force of habit. You want to keep your variables consistent. And if we multiply this out, we get 2 equals as cubed plus bs squared plus 2as plus 2b plus cs cubed plus ds squared plus cs plus d. If I look at the s cubed terms, then I get a plus c equals 0. If I look at the s squared terms, I get b plus d equals 0. If I look at the s terms, then I get 2a plus c is equal to 0. And if I look at the constant terms, then I get 2b plus d equals 0. Now, as in the previous example, the two equations, the first and third equations, together imply that a and z are both 0. The second equation implies that b and d are opposites. Oh, excuse me, this should be 2. 2 for the constants on the far left. And if I plug that into this equation, the fourth one, then I get b is equal to 2, and therefore d is equal to -2. So scrolling back up, that would imply that this first fraction in my inverse Laplace transform can be decomposed into 2, since a is 0 and b is 2, 2 divided by s squared plus 1, and then we have -2 for d, c being 0, -2 divided by s squared plus 2. To find the solution, now all that we need to do is find the inverse Laplace transforms of all three of the functions which are being added together in this parentheses here. And as usual, we're going to turn to the table. The table, which is going to tell us what to do with number divided by s squared plus number squared, and s divided by s squared plus number squared. So now it's time to start fussing with the functions that we're trying to inverse transform so that they match the entries in the table exactly. For example, in our very first fraction, we have number divided by s squared plus 1 squared. So to match that, we should really have a 1 in the numerator instead of a 2. So what I'm going to do is I'm basically just going to move that 2 to the side, factor it out so that I have a 1 up there. In the second entry, the second fraction, we have number divided by s squared plus the square root of 2 squared. That's equivalent to the number 2. To match that, I should really have a square root 2 in the numerator. So I'm going to take the 2 that I have currently, and I'm going to split it up to have 1 root 2 in the numerator and then a second root 2 off to the side. In the last entry, we have s divided by s squared plus number squared, but we have an extra copy of 10 in the numerator. To fix that, I'm just going to move that 10 so that it's a constant multiple off to the side. And having done that, we can now use linearity and the entries in the table to find the solution. 2 times the inverse times sine of 1 times t minus square root 2 times sine of root 2 times t plus 10 times cosine of 1 times t. So this function would be the solution to the initial value problem that we were given. Now some of you may look at the initial value problem that we were given in this exercise and say, but wait a minute, Sam, that's a second order constant coefficients differential equation with a trigonometric function on the right side. So why couldn't we, just guess a solution of an exponential format to solve the homogeneous part of this equation, find the complementary solution, use method of undetermined coefficients to find a particular solution, put them together, and then use the initial conditions to find C1 and C2. You can totally use the old-fashioned process to solve this particular initial value problem. That's absolutely correct. And at the moment, because you're new to Laplace transforms, the old method will probably be faster for you until you get used to this new method. But I find that Laplace transforms scale a little bit better to more complicated problems. Laplace transforms are really also the only tool at your disposal when you're working with a function on the far right side, which is not so simple as a trigonometric, exponential, or other function, but Laplace transform can actually be used when the function on the far right side is piecewise. That's one of its greatest strengths, is that it can deal with a piecewise function on the far right side. And that's the situation that we'll be talking about over the course of the next couple of days. That concludes today's material. We studied how to calculate the inverse Laplace transform of a function. Usually it involved reworking the expression so that it matched something in the table that we have, and then using that table to find the inverse Laplace transform. Then we practiced using the Laplace transform to solve an initial value problem.